Hi everybody, hallo alle zusammen. Welcome to the lecture of Fundamentals of Video Technology. My name is Gerald Schuller. Mein Name ist Gerald Schuller und diese Vorlesung wird zweisprachig sein. Zum einen Englisch und zum anderen Deutsch, und die Folien wird es auch in beiden Sprachen geben. So this lecture will be bilingual, and that's why we have the lecture slides in both languages, German and English. And you can find them on our external website, or the most up-to-date ones are in Moodle. Die Vorlesungen werden also in Moodle abgelegt, die Vorlesungsfolien in beiden Sprachen, und die Videos werden dort auch verlinkt. Die Videos werde ich dann auch in YouTube hochladen. So this is our Moodle 2 webpage. So this is where you can find all the announcements and also the slides for the lecture. Right, so here you can see it. This is the Moodle page, and here are the descriptions. Here are some useful links, like the Python programs we are using, a Linux tutorial, because all the software we are doing is in Linux. Here a Python tutorial in case you're not so familiar with Python, which I assume is true for most of you. So please go to this link and go over it, practice it. And you can also install Python on Mac. So basically it works best on Linux, so we will only support Linux operating systems. And Mac OS is also a Unixoid operating system, so it's quite similar to Linux. So basically you can use the same shell commands. And terminal or shell is what we use for our programming and executing those programs. So you should be familiar with shell commands, and this is why we have this link here. Right. So this also shows you the shell commands. Yeah, and here you can see when you go down, you have the different lecture slides. So like here, and here is also the place where you will find the links to the videos. And here you have Nachrichtenforum. So this is where we make announcements, and this is also where you can ask questions to us and to your fellow students. So when we click on it, you can see a list of announcements that was made by me or fellow students or by Oleg Golokolenko. And Oleg Golokolenko is our course assistant. Right, so basically Moodle 2 is our communications center, and this is also where you can ask a question if you like. Also, at the end of the normal time slot for the lectures will be question and answer sessions, which I will also announce here in the news forum. So usually it's like half an hour question and answer. So after you looked at the video and you have questions, you can go to the question and answer session, which will be live, and ask those questions and listen to the answers that I will give. Yeah, so this is an important link for us, especially in this online version. So everybody needs to enroll in Moodle and enroll in this course here in Moodle. Yeah, so this is probably the most important part here, the Moodle 2 website. Yeah, so here's the link. And also in Moodle 2 we will have quizzes after the lectures, which is short tasks which you need to answer and which will give you points as part of the seminar points. So the seminars are then based on Linux as an operating system. It could be, for instance, the Raspberry Pi microcomputer, but it most often probably will be your laptop running with Linux as operating system. So Linux is also important because we only support Linux here and because things work best in Linux in our experience. Basically, Python you can also install on Windows, but sooner or later you run into problems which we also cannot solve, right? Like if you have some more advanced module, often they cannot be installed in Windows, but only really work in Linux. Yeah, so that's why I recommend to have a laptop in dual boot mode. So you have Windows in one partition, and then you have Linux in another partition, and when you start the laptop it asks you if it should be in Linux or in Windows. And this is actually relatively easy to set up. Just download for instance, Linux Ubuntu ISO image from the website or from Ubuntu's website, and start it from either a USB stick or from a CD-ROM, and then it will start and install it as a dual boot on your laptop. So that's actually fairly easy. Yeah, seminars will count 30% of the final grade, and the final exam would count the remaining 70%. And the first homework assignments will help with practicing or revising the Python concepts. So this is basically just getting you started. Everyone should have a Raspberry Pi or a computer with a Linux distribution installed, as I just said. Ubuntu is relatively easy to install and much more user-friendly when it comes to programming rather than Windows. Right. Also, Windows causes too many software problems. Ubuntu is the most popular Linux distribution available and can be installed next to Windows as dual boot. So, for instance, using these links here. These links, I think, are a little bit too old. So 2015 and 2014 is probably no longer up to date. Yeah, and then as part of the seminar, programming homework assignments will be uploaded on Moodle 2. There will be short quizzes in Moodle 2, as I just mentioned, after each lecture, which counts 25% for the homework. And of course, you should register in Moodle 2, and will be available weekly after every lecture and should be done in 1 week. These homework tasks are an integral part of this course. This is the only way to get the concepts to acquire the required skills for building video systems. So basically, you want to acquire a skill, and a skill is acquired by practicing. Yeah. Let's make this a little simpler. It's the only way to acquire the required skill for building video systems. Okay. So the course has a total of 4 credit points. Each credit point is about 2 to 3 hours of work per week. So altogether you can expect about 8 to 12 hours work per week. So that includes everything, lecture, seminar, and homeworks. So that also shows that the homeworks, you should plan sufficient time for the homeworks. Homeworks are programming assignments, and programming takes time. So actually writing the actual program actually is usually quite fast, but what will take most of the time is the debugging, right? It never runs the first time, but you always will have some errors, and then you need to figure out where those errors are and then fix them. And this is actually probably the most important skill of programming, that you actually that you know how to find the bugs in your code. So finding the bugs is actually your tasks and not ours, right? So important skill for programmers. or for software engineering in general. So note, for every week around 3 hours will be for the lecture, and therefore the remaining 5 to 9 hours will be for the homework, or about 1 working day per week. So this is what I just said. So note, the scripts in the copy shop, if they are in the copy shop, they are not up to date. So the most up-to-date slides will be available in Moodle 2 and possibly also the outside website. The lecture slides are not a replacement of a course book. They are just a guide for self-study and not as a complete source. For self-study, the slides contain the references to books and website. So actually you should take a look at those references that I'm giving from time to time in the lecture slides. Right. So not a replacement. And the slides are deliberately kept in editing mode because they are supposed to function like a blackboard. So as you just saw, I like to make edits to them. Originally those edits were for giving or including answers to your questions, but it's all since you cannot ask questions live, basically I'm thinking of some better explanation and then adding them here. Yeah, so in this way we can respond flexibly to questions from students and answer the answers at the same time. One of the main aims of the lecture is to answer questions, well, or at least questions I can imagine. The latest versions of the slides will be then uploaded on Moodle 2. So the general goal of the lecture is to present new knowledge, and the general goal of the seminar and the Moodle task is practicing the knowledge to acquire the skills for applying them. Right, so both is needed. First you need to get the knowledge and then you practice it. Yeah, and the goal of this lecture is to learn about the techniques and principles of wireless transmission of video streams and audio streams. For example, the Raspberry Pi, we try to have a transmission of an image using sound. And this is also a practical example. You transmit an image from A to B, and this is basically the entire chain of video technology, from capturing to processing, coding, transmission, decoding, and then displaying on an image, on a display. So this is this Raspberry Pi example will be a simple example where you can see all those parts working. And I think having examples is always the best way of understanding something. And actually in my case it will not be the Raspberry Pi, but of course my laptop running Ubuntu, or perhaps my little iPod Touch, which runs the Mac OS or the iOS. So here at the content overview, first an introduction to Python, since I assume that most of you are not that familiar with Python. So this includes Python basics. Then I will go on to psychophysics, which is the properties of the eye. So the eye, and also the properties of hearing, just a little bit. Then finally in the end, or towards the end, we will also cover digital filters and digital transmission. Right, so this is important for transmitting the image from A to B. Psychophysics, the properties of the eye, is important for compressing an image to reduce the data rate. Yeah, so that lets us start with history. So the history is actually also, I found, useful to give an impression of what principles are behind this transmission chain in video technology, right? So each critical part needed to be invented at some point. So when you look at this list here, this German list, you see in the beginning there's actually the discovery of light sensitivity of some material here, selene. So this is basically the fundamentals of a video camera. You need to have some light sensitive element. So this was the discovery of the fundamental effect. And then here you have the first usable photosensitive cell. So that came a few decades later. Always takes some time to obtain a product. Then here is already a first attempt of transmitting an image, and as display here 2500 lamps were used. So each lamp is a pixel, right? So that's not really practical, but this was showing the principle of decomposing an image into pixels. Then here Nipkow towards or in 1884, Paul Nipkow then invented the serialization, so basically transmitting pixels sequentially. So he used a disk with holes in it, with tiny holes, and those holes then were running over the image line by line, and that means at each time point those holes were just covering one tiny piece of the image, one pixel, and the light intensity was then transmitted. So the light intensity was transmitted serially, one after the other, and that was the basic invention here. And this was mechanical because at that time there was no electronics, and that's also why this had limitations. A disk can only rotate that fast. Right, and then came the electronic era. So here Edison, he discovered the emission of electrons from a hot wire, which is the fundamental of tube amplifiers and also for cathode ray tubes, right, Brownsche Röhre. So this was important for displays. And the tubes here, Lee de Forest invented the electronic tube. That was important for electronics, right? For electronics, you could amplify signals, process signals, transmit signals using transmitters. So here you see the first ultra short wave transmitter, so FM transmitters. So they were necessary because they could cover the necessary bandwidth of video. So here it was continued. Manfred von Ardenne had a broadband amplifier. Then here in 1933 was a transmission of 180 lines and 25 images per second. Here then first public transmission as the for the Olympics in 1936, the infamous Olympics. And from there it continues. And even in the Stone Age, you already had some predecessors of it, basically cave paintings, right? You have an illustration of 3 dimensions, say a hunting scene, and you then transmit it or put it on the wall, which means you have to do it with a 2-dimensional surface. So that means we need to have a mapping from 3 dimensions, the real world, to a surface of a wall, which is 2 dimensions. And this works because the brain can basically reconstruct the original 3D scenery. So maybe this should be reconstruct. So this is actually also an important principle when you think about it. Each camera does this transform from the 3-dimensional world to the 2-dimensional surface of, say, a CCD chip, right? And this only works because the brain can then reconstruct the original 3D world from just those 2 dimensions. And that's basically working because the human retina in the eye is also two-dimensional, right? You have a surface area, and then the brain needs to reconstruct the information from the real world. Yeah, then in ancient Rome, we had wall newspapers. So at those times they didn't have printing presses yet, of course, so they needed to handwrite those newspapers, and in order to for many people to see it, they put it in some central square of Rome, where many people passed by. And that was the first mass media, right? Announcements or information to many people. Yeah, later, when you had the printing press, you had book printing, you had a more wide distribution, so over a wider area, more distribution, and also over wider area, because you could transport those books. And in modern times, we start with a pinhole camera, where the pinhole was a predecessor of a lens, right? So here you can see it. Here you have an object, this arrow here, and then you have this screen here, where you have a tiny hole in it, and then here you have the display screen. And when you follow the light beams coming from the object, you can see they cross here in this hole, so that the object reappears here but upside down, right? And the size of the hole determines how sharp the reproduction will be, or the projection. So you want to make this hole as tiny as possible for a sharp projection, but then you have less light going through, so it needs to be compromised. Yeah. So actually in the beginning, people were using this for drawing by hand. Later they had light sensitive film here. Yeah. Yeah, so later this plate was replaced by lens for more light. So here, when you make this opening larger, you get more light, but then you have blurriness, and you can fix that by placing a lens here. Yeah, so this is then the projection, 3D to 2D, and then you can actually scan this projected image, right? For instance, using photocells, you can place many photocells across the screen here, each photocell covering a tiny area, a pixel. And then this photocell determines how much current is going through it. And the current is determining how much a lamp is lighting up on the display. And then we have a transmission. So for instance, if you have 2,500 of those pairs, then each pixel is connected to the corresponding lamp on the display, and you have a transmission. But that, of course, is not really practical, because for each pixel you would need an individual line pair. Still, it would work because the brain or the eye interpolates every individual pixel into a connected image. So to avoid the many pairs of wires from the camera to display, we do a serial transmission. So here's the Nipkow disk. So here you can see the little holes, and this rotates, and for each little angle here the hole rotates over our screen, and when one hole passed, then the next little lower hole comes and covers the next line, and then line by line we have a transmission. And that's why you have this spiral path here, because after each segment you get a next hole which is a little bit deeper until the entire screen is covered. And then, of course, on the display side we have the inverse problem. We need to project the light intensity at the right point on the screen. So here again we have a lamp, but now this lamp shines the light through the corresponding hole, which is then projected on the screen. And when this disk rotates simultaneously and synchronously with one on the camera side, then the light the light pixel will appear at the same position as on the camera side. Right? And if this is fast enough, then you don't see the point covering this screen one after the other, but it will all appear as once. So here you have a moving picture if those disks are rotating fast enough. So basically it's possible, but still you get only very few lines. You can see here the disk has only space for so many lines. So that's why the quality is actually quite low. So the principle is still used. So we not only have local interpolation, but also temporal interpolation. So this should be spatial interpolation, because here we have the different lines, right? We have one line above the other, and then it's basically sampling the space, and that means our brain needs to interpolate those lines. And also we have it in temporal direction, since the light points goes over the image one after the other. It needs to be fast enough. So the rapid flickering is perceived as constant light. Therefore, we have a reduction of complexity and cost, but limiting this mechanical system is that we only have a few lines and a few frames per second, hence a low quality. So that's why it's done electronically, using first cathode ray tubes and later digital cameras and displays. For the transmission over the air, we need a high carrier frequency because the required bandwidth. Right? We have many changes of intensity per second, and that means we need to have a high bandwidth. Right? Remember, it needs to be fast enough for the eye to not see that it's just moving points one after the other. So we need to have correspondingly rapid changes of intensity, and that means high bandwidth on the transmission over the air. So in analog TV, we need about 5.5 megahertz bandwidth for the analog TV standard. And so when you see analog TV, you see it's not really sharp compared to digital TV, but still it needs 5.5 megahertz. So it's actually quite a lot and much, much larger than for voice or speech transmission. Right. So that's why we need high frequencies. So usually we use the ultra high frequency band, which is in the frequency range between 470 to 690 megahertz. And so the total band has about 200 megahertz bandwidth, and that's enough for about 40 TV channels. Right. So that's the usual band. And actually with the switch to digital, in 5.5 megahertz bandwidth, which is one analog channel, you can usually fit about 4 digital channels. So that actually gives you an extra boost in the number of channels that you transmit. Plus, in digital, you can have one frequency network, which means one station has the same frequency all over a country, unlike analog, where neighboring transmitters in the same country need to be on different frequencies to avoid interference. Black and white television came to the US in the 30s and 40s. It started in Germany during the Olympics in the 30s, but then was disrupted with the Second World War. In the US, the development continued somewhat, more or less, and in Germany it became widely established in the 1950s. And then also in the US was developed the color TV, the next step, right? And what's used there is that the eye has only receptors for three different primary colors, right? Our eye only has three different cones, red, green, and blue colors or wavelength ranges in the visible light spectrum. So you can see it here. So here, this is the electromagnetic wavelength spectrum. Here's the wavelength. And the highest wavelength produces red impression from the eye and the brain. Then a little bit lower band wavelength produces the green impression, and the shortest wavelength produces the blue impression. And we only have those three types of sensors, and all the other colors we can see are the result of the mixture of those three. So if those cones in the eye have a different proportion of those three primary colors, we will perceive mixture colors. So that's good, because that means that any color can be represented as three primary colors in different mixture relationships. So just the three primary colors need to be transferred or transmitted. And the spatial and temporal resolution of color perception is less than for the brightness. Let's say for brightness perception. So for brightness, we have different cells in the eye, the rods, and they have different properties, as we will see. And that also means the required bandwidth for color information is less than for brightness information. And that comes because the eye has many fewer cones than rods, right? The color-sensitive cones are much fewer than the intensity-sensitive rods. That's why the bandwidth can be less. So the lower bandwidth makes it possible to embed the color information into the gaps of the black and white signal. So that's good for backwards compatibility with black and white TV. So when the color TV was introduced, there were also already many black and white TV sets, and they wanted to keep the new system backwards compatible so that the old black and white receivers can also watch color transmissions, although in black and white. And that proved to be very important for the introduction of this new system. So later came digital TV in the 2000s. It's based on this new standard, digital video broadcast, and this is not backwards compatible because digital is quite different from analog. So there were actually attempts for radio to be backwards compatible to analog, but it's always a compromise in quality and available information or available number of programs. So it didn't really take off. So what took off is just using digital video broadcast transmissions on the analog spectrum. So the UHF spectrum is still used, the same channel spacing is used, just that instead of one analog program, we now have 4 digital programs on that same channel. So actually you could argue that it's partially backwards compatible by using the same frequencies and the same channel grid. So that's what I just said, it uses the same frequencies and channels. And for the old TV sets, you could get set-top boxes for the conversion into analog TV. They were relatively cheap, so you just have the set-top box, and then basically it decodes your desired program and then outputs it in an analog way to the antenna input of the analog receiver. So in the meantime, there are not many analog receivers out there, so it's not really necessary anymore. Yeah, and this started in Thuringia in November of 2005 and in Berlin already in 2002, the digital broadcast. It uses higher information density of digital transmission, so one analog program is replaced by 3 to 5 digital programs. So let's say replaced. Okay, that looks better. Yeah, so when you look at the resolution of analog TV, it's approximately like on computers the old VGA standard, right? And these are the old displays, and they are actually not very sharp. And exactly you get in 50 hertz countries, which means you have 50 hertz power frequency, so that comes out of your power outlet. You have alternating current, and in Europe and Asia and Africa you have 50 hertz frequency of the power coming out of your power outlets. In the Americas it's 60 hertz, right? Slightly different. And for the old analog TV sets, it was important to synchronize the pictures, the picture frame rate to the power frequency because of the cathode ray tubes. They were controlled by big magnetic fields, and the power transformers of the TV sets had transformers which generated 50 and 60 hertz magnetic fields, and in order to avoid noticeable interference, they were simply synchronized in frequency. So in the picture, when you have a static distortion, it's not very visible, but if you have moving distortion, this becomes very visible. So that's why they chose it to be synchronous. So here you have the frame rate, 2 half pictures is exactly the 50 hertz. Here the frame rate, 2 half pictures is also 60 per second. So it's synchronized. So that's why you get slightly different number of lines, because the number of lines per second should be similar, right? So if you have more pictures, you get fewer lines. So in 50 hertz countries, you have 625 lines. In the Americas, you have 525 lines. So it's actually just a tiny difference which you don't really see. Yeah, and the numbers of lines per seconds is important for the transmission bandwidth. And because you want to have a similar transmission bandwidth, you want to have a similar channel spacing, that's why you want to keep the number of lines per second constant. Yeah, and here you want to avoid artifacts from the magnetic fields of the power supply. Yeah, and it's all not necessary today anymore because we don't have cathode ray tubes anymore, and we have switch power supplies which have much weaker magnetic fields and at different frequencies. Yeah, and then we have HDTV. So the analog channel is now replaced by 3 to 5 digital channels or programs of the same resolution in standard definition TV, but for HDTV, high definition TV, it is replaced by 1 digital channel of higher resolution. Right, so then we use the additional information rate to improve the resolution. Yeah, and then the resolution is approximately like modern computer monitors, and HD TV televisions are also widespread nowadays. So usually when you have a TV set which is not too old. You can easily use it as computer monitor because it has roughly the same resolution. Yeah, and the operation in the meantime is widespread in digital video broadcast. And also techniques for recording, transmission, and playback is available. So actually digital processing, recording, transmission is much easier than in analog. So let's take a look at common monitors, like in your laptops, PCs, or TV set. They all work with the same principle. So here I have a close-up using a microscope connected to a USB input of my laptop, and this is what you will see. You can see 3 stripes for each pixel with the primary colors, right? Red, green, and blue. And each of those stripes can be controlled in intensity separately. And the mixture then determines the color that we see at some distance. So here when we're close by, we just see those 3 colors because they don't mix, but when we are further away, those colors mix in our eye, and then we see the mixture colors. Yeah, so here you can see it even closer. So here's what I just said. Each pixel, which means picture element, consists of 3 short strips of the primary colors. And the colors of the pixels are created by color mixing, depending on the proportion of the 3 primary colors. And each pixel represents a small color point of our image. The principle of color mixing is also found in book printing. For example, I use the same microscope on a printed color image, and then it looks like this. So instead of pixels lighting up in different primary colors, we now have paint in different colors, and you can see when they overlap, they become darker, and this means they absorb more light. So paint work with the principle of absorbing parts of the light spectrum, and that makes them colorful. And that's also why we have different primary colors here, because this is the principle of subtracting color mixing, right? So our display is doing additive color mixing. It adds lights. Here we have subtractive color mixing. It means we subtract different parts of the spectrum. Yeah, so now to a brief introduction to Python with NumPy and SciPy. But note, this is not a course to introduce Python, but a course on algorithms that are implemented using Python. Knowledge of Python is therefore required. The following is a brief introduction for those who need a quick introduction. So basically, you should learn Python by doing it, and this is in general a good approach for learning a programming language or any language for that matter. So Python is a powerful object-oriented programming language. At the same time, it does not need to be compiled, but can be interpreted at runtime. It also has a convenient command line interface, making it easy to try out a few program lines. So it's like before you put something in your file with a program, you just type it and see what it does, if it does what you expect. And that's most of the time also a good approach. You first test a command to see if it does what it's supposed to do or what you think it does. Yeah, in addition, there's an enormous variety of program packages or libraries for it, and everything is in open source. Actually, it's called modules in Python. Yeah, and it's important that everything is in open source, which means you can freely download it and also contribute to it. So it actually lives from people contributing to it. So with the command line interpreter IPython and the packages NumPy, SciPy, and Matplotlib, the operation is very similar to MATLAB. So if you know MATLAB, then this is basically a subset of Python. MATLAB, however, is a commercial paid program. In addition, Python is more powerful because it's actually a full-fledged programming language. For instance, it can process audio and video streams in real time, which is not the case in MATLAB. So here can be processed in real time, which is not the case in MATLAB. Yeah, Python NumPy and SciPy are packages that are very similar to MATLAB in the sense that they cover the mathematics, right? Which are generally used in digital signal processing and therefore also for digital video technology for the calculation, simulation, and implementation of algorithms. Because of the wide distribution and the importance of the ability to program in MATLAB, or here in NumPy and SciPy, it is also used for our homework. There's also Octave, which is the open source version of MATLAB. However, it is a little bit slower and a little bit less comfortable. For non-real-time and non-video computation, it is still very comfortable, but because of its limitation, we will use Python. So in Python, we can actually make a real-time video processing. For example, we want to have a picture taken and then transmit over a distance using sound. So this can actually be done using Python. We can have direct access to the camera, take a picture, process, and so on. NumPy and SciPy are the packages that run under Python. They are open source and can be installed directly on the Raspberry Pi or your laptop from the Software Center as Python NumPy and Python SciPy. So you would type, for instance, sudo apt install Python NumPy. Maybe I can add that here. Non-volt. Sudo apt install Python SciPy. Right. So since they run under Python, they also have the extended capabilities of Python, such as video streaming for recording and playback, which we want to use. And this is in the terminal shell. Terminal shell. And IPython minus PyLab gives you an environment which is quite similar to MATLAB. So it gives you an comfortable shell for typing commands, for instance, including auto-completion and with colorful prompts. And it also easily lets you plot, for instance. So this minus PyLab automatically loads NumPy and matplotlib and then runs. And you can also install IPython using this command here. So this is also what I just showed for SciPy. Maybe I can also make this a different font here. Yeah, so after you install IPython, you can then start it from the terminal shell. So let's say terminal shell. It has different names. Sometimes it's called terminal, sometimes shell, sometimes console. They all mean the same, right? Yeah, so here you have this addition, this minus minus pylab, this option, and that means it automatically includes everything from NumPy or from matplotlib. Right, so this is equivalent of first starting IPython and then running those imports. Here, those two. So this means it takes the module NumPy and imports all the modules, all the functions it has in the working space. So the star means there is no naming of the library, which is always kind of dangerous. And so I actually discourage this from import star. So you can do this for short sessions for convenience, but in general, basically, you should avoid this kind of import. Yeah, so this shows a way of importing libraries, which directly imports all the functions of the library. The most important or the most interesting mathematical functions are in the library NumPy, and we can also use them with this import. So this is actually what I recommend. Import NumPy as NP. So NP is then the abbreviation for NumPy, and any function from NumPy you want to use, you have to prepend an NP dot to it. So for instance, the sine function you would call as np.sine. Yeah, so this is an abbreviated form. And this is useful because if you have, for instance, also the library SciPy, this also has a sine function, but with somewhat different handling and somewhat different functionality. So then you can only distinguish them by prepending this abbreviation. Yeah, so this referencing of the library has the advantage that we can distinguish functions of the same name from different libraries. So otherwise that might be a cause of bugs which are difficult to find. Yeah, if we want to access all functions, we would use this from import star, which I don't recommend. Yeah, Python basics. So on Ubuntu, start a shell console via menu or with a shortcut. Don't know why this is there. So here the shortcut is Alt-Control-T, which only works on Ubuntu. Then enter Python, followed by the return key. Yeah, and also observe that basically there is Python 2 and Python 3. Python 2 is outdated nowadays, so we should use all Python 3. Right, so don't install Python 2, install Python 3. Yeah, so once we have it installed, we can open a shell and just type Python, or if you have both installed, you would type Python 3. Right, so I can actually show you. Alt-Control-T gives me this shell, terminal shell. With Control plus I can make the font bigger so that it's easier to see. And now you type Python 3 to open Python 3. So in my case I have to add the 3 because I also have the 2. So here this now opens Python 3, and you can see now we are in interactive mode of Python, right? So this is now a different prompt, and it shows you now we are in interactive mode of Python 3. And now we can enter Python commands. For instance, we can use it as a calculator. So 1, 2, 3 plus 4, 5, 6, right? And when we type enter, it actually calculates the result. Or 2 times 3, 6, or 2 to the power of 3 is 8. And here you can also see the specialty of Python, that the exponentiation is not an up arrow, but 2 stars, 2 multiplication symbols, right? That's the exponentiation. And this has sometimes advantages, because this up arrow is often at different places on the keyboard. It's a special symbol. Right. So when you use IPython, you get more functionality, for instance auto-completion. So here I don't have auto-completion. When I use the tab, then it's not completing. So let me try IPython. So now when I'm exiting, you have to enter the function name quit with empty arguments. So this actually lets me end this session, right? Quit with empty brackets. So now I'm back at my normal terminal shell prompt. So now I can also start IPython. Let's see if I need a 3. Yeah. So here I have IPython 3. So again, the 3 to distinguish it from the 2, which is also on my computer. And now we get this colorful prompt here, right? So now you can again do those computations. Same thing. Same thing. But now I have auto-completion. For instance, if I want to repeat the first line but modified, I just start with, say, 1, 2, and then I use the tab, and then it's not doing it. Interesting. I need the up arrow. So auto-completion is done using the up arrow on the keyboard. So then I basically automatically get this line back, which starts with these characters, and then I can also edit it with a backspace, for instance, like this, and get a new result. So that's convenient, and it also has some other niceties, but you don't really need it. It's just convenient. Yeah, so this opens the interactive mode. Yeah, important is also here this help. So when I go here, I say help, and then a function name, for instance sign. And here you can see sign is not defined because we didn't import it. So first we need to import numpy as np. That's where the sign function is. And then I go up with my up arrow and then say np.sign. So this is where it can now find the sign function. And now you get the help function. And this is often very important for functions where it's not very clear what arguments it expects. So here it's actually easy, but in general it's not so easy. Yeah. So here it explains the arguments and the returns. It also tells you what it returns. Yeah, and this is actually a common help for many functions that you can see here. So let's see if I can actually find the sign using. Oh, great. Yeah, sometimes it has too much information. So actually what's not so straightforward is that the argument of the sign is in radians. So from school you might know that the angle is between 0 and 360 degrees. Here it's in radians, which is between 0 and 2 pi. Right? Then 2 pi corresponds to 360 degrees and pi corresponds to 180 degrees. So you can see it here, np.sign. So 3.1415. So this is approximately pi. So this is approximately 180 degrees. So we remember sine of 0 was 0. Sine of 90 degrees, which is pi over 2, is 1. Then sine of 180 degrees or pi would be 0 again. So this should be 0. And we see this is the result. Here we see as a result 9.26 times 10 to the minus 5. So this e to the e minus 5 means times 10 to the minus 5. So 10 to the minus 5 is a very small number, right? Remember, 10 to the minus 5 is 1 divided by 10 to the 5th. So it's 10 to the 5th is a 1 with 5 zeros. So correspondingly here you would have 5 zeros in front of the 9 here. Right, so it's a very tiny number, and it's not exactly 0 because this is not exactly 180 degrees. And also this function has limitations in the accuracy. So actually we can use exactly pi, or say more exactly, and this is what we will get. So here's np.pi. So even this np.pi only has limited accuracy. So pi is actually infinitely long, which we don't really have. Remember, this is not a symbolic math package, it's numerics. It's all numerics. And numerics only has limited accuracy. And here we can see the limitations of the accuracy that Python is producing. So here this should be 0, and instead we just get 10 to the minus 16th. So this also shows the limitations of accuracy of Python. So 10 to the minus 16th is generally a good estimation of the limits of accuracy. Yeah, right. We also have assignment. Here a equals 1 plus 2. A equals 1 plus 2. So now we don't see the result, but it's stored in the variable a. And we can simply type a here in the interactive mode, and we get the content as 3. In a program we would write print a, because there we are not in interactive mode. And again we get the result of the content of a. We can also test for equality with 2 equal signs. So this is for an if statement. So say b equals 1, and then we say a equal b, and it tells us it's false. If b equals 3, we test it again, then it's true. Right. Yeah, so in Python we also have the library OpenCV, and there an image is represented as an array, and one pixel consists of 3 values. So we have 1 value per primary color. So an example for an input of an array for a black and white image here. So here we just need the intensity. Here we just need a 2-dimensional array. Right? So here the first row, here's the second row. You can see it tells you the type. This is an array, actually a NumPy array, as you can see down here. And the argument is the entries for this array. So here you have the first row, here you have a second row. So this is a 2-dimensional array. And this is basically like the image, right? The image has rows and columns, and this is what you see here. Here we see the different rows. So for a color image, not only brightness values appear for each pixel, but an array of 3 intensity, 1 per primary color. Should be primary color, right? Yeah, and then basically we have a 3-dimensional array. So here you can see it. Here's a 3-dimensional array, and basically each of those triplets is then a set of primary colors. Right. So basically we place each of those entries of float numbers now by a one-dimensional array of 3 numbers, each representing the intensity of the 3 primary colors. So for instance, we can address pixel number 00 by specifying C, and the argument has then rectangular brackets 0, 0. That gives us the primary color intensities for this pixel. So here 1, 2, 3. Right. We can also specify the primary color by appending another index here, index 2. So for OpenCV, this is for red. So then we have the 3. Yeah, also important is that Python distinguishes between arrays and matrices. So there's also a matrix type, and the matrix type is mainly important for mathematical calculations involving matrices. So in general, I'll try to avoid the matrix type because it easily causes confusion. So here's the matrix type. So here, for instance, we can mathematically add 2 matrices. In this case, it's identical to the case of an array, element-wise. But what's different is multiplication. So matrix multiplication is different from array multiplication. Array multiplication is again element-wise, but if you have the matrix type, this is the mathematical matrix multiplication. You can also get the element-wise multiplication with the matrix type using the function multiply. And this shows you the possible confusion that can come up, right? Depending on the type, you have different behavior for the multiplication, for instance. You also have the inverse of a matrix. This is actually an advantage of the matrix type. It has built-in inverse. Here you have the inverse of the matrix, and in object-oriented representation, so here this is object-oriented representation, we get a dot I. So I is a function of the object A. We can also take a look at the shape, which gives us the dimensions. Shape of A as a function, or again as a object function of this object A. Yeah, then we can easily make Python scripts. As you can see here, you have a little formula, and then you can create a file with the extension .py, for instance, test script. So I can open it, copy, quit this interactive. So for this you have to exit the interactive mode. You go back to your shell and open an editor. So I'm using gedit. I like gedit. It's on Ubuntu. It's by standard. It's installed by standard. So then you just give it the name. If the file exists, it's opening it. If it's not existing, it opens a new file with that name. So you can see it. Yeah, indeed, it's not existing. So it's opening a new one. So it's important to have an editor and not a word processor, just as Word or Writer, because they don't store the ASCII code of your text. They have all kinds of additional information. That's why you need to have editors. Editors only store the characters that you enter, nothing else. And this is also what Python needs. So I recommend gedit. If it's not there, you can install it using sudo apt. The get is not necessary anymore. And then you can enter, for instance, this little script. So I just copy and paste it. Control C, paste, right? And then I can say save. Save, here's the save button. You can also use Control S. So now you have this test script written and saved. So here this shows you how to add a command. So the double cross basically makes this command. Python ignores the rest behind it. Here I assign variables a, b, and here I compute a result, y equals 2 times a plus 3 times b. And then I print the result at the end of the program or the script. So now I'm done. So I have saved it, and we can check it using ls, for instance ls test star.py. So this also shows you how to see files in your current directory. So here you have ls for list, right? This command lists everything which starts with test, then has arbitrary characters here for the stars, and ends with .py. So you can see it. You can also see, say, or type ls -l for long, then you can see more information. And here you can see it was written 11:14, which is around now. And it has 58 bytes, right? So a tiny file. So basically 58 characters. So now we can also take a look what's inside, just for checking, right? By using the command line tool more. So test script. So I'm using tab to autocomplete, more test script, and this just lists the content of this file on the terminal shell screen. So here you can see it. So here's what we just entered. So we confirm that it's really there, right? It's not lost or something. Yeah, and then we can execute it using this command line. So we start on our terminal shell. Now again issuing Python, so I should use Python 3. And then instead of hitting return, you enter as argument the name of the file you want to execute. So here it is test script.py. Right. You can also use autocomplete, the tab as autocomplete for convenience. And here we have, interesting, already an error. And this is what you usually will find when you execute your file. You will get some error message. So what you do then is you closely look at the error message. Here it says syntax error, missing parentheses in call to print. Did you mean print with parentheses? Question mark. And actually, yes, indeed. And this is an error because print was a command in Python 2, but it became a function in Python 3, which means now the brackets are necessary. In Python 2, they were optional, but in Python 3, they are necessary. So that means we need to go back to our editor. So gedit. So I'm opening it again. And now I include my brackets and Control S for saving. I leave it open just in case we have another error, and up arrow gives me the recent command. Now return for executing it again, and now I'm happy because I'm getting an output 23, and this looks about right. So this is how you should do it. This is how you can execute Python scripts. Yeah, it seems the 23 was correct, so that's good. Yeah, when we have longer programs, you want to have functions, and we can easily define a function in Python. To do this, we write a file with the name testfunction.py, which contains our function. It can also be several functions with a content def, and then comes the function name. Then in the brackets come the arguments of this function, and then colon. Colon finishes the header. And then comes in comments the help text. So this is the text that appear when you say help my function. Right? help is a function, and you put your function name as an argument to the help function, and you will get this text. So this is the help text for my function. And you can see you can also use 3 parentheses as command sign. This is actually a multi-line command. So the double cross is only for this one line in which it is in front. When you have multiple lines as a comment, you would use those 3 parentheses in the beginning and the end. Right? So this is particularly useful for help text because often this goes over multiple lines. So here you have the same computation, except that A and B are not fixed as in the previous script, but they are arguments, so you can change it each time you call this function. So this is usually the advantage of a function, that you can call it with different arguments. Also note the indentation below the function declaration. This has in Python the function of parentheses. So in Python, this has the function of parentheses. So that basically marks a block. Yeah, so let me try this. Test function.py, copy. So I go back to my terminal shell, gedit, then paste, and then ampersand. Ampersand just makes sure that my terminal needs still stays usable even after I start gedit. So here I can actually still use it. And here I can just now copy and paste this text. Copy, paste. Right, and now save it. Save. So now we can also use more. So instead of gedit, I'm now using more for checking. And indeed, the text is there. So now we can use this function as part of another program. Right. So we can now use it in another program, or here in this case, we use it in IPython. That's also possible. So I start IPython 3. And here to now use this function, we need to have it imported. So I say import test function. I abbreviate it as TST, right? Oh, interesting. Oh, Testfunktion has a different name. Huh, interesting. So this should be Testfunktion, the German name. So, yes, now it worked. So here you can see another error. It didn't find this test function, and the reason was a typo, right? That can easily happen. So now we imported it, and we can now use it by calling this function with prepending, in my case, the abbreviated module name. So here it became a module, so I would call TST for the library or module name, and then my function, say 7,8. So in principle, like the sign function, just with 2 arguments. Yeah, it works. So here the output is correct. So that's nice. And this is also how you would do it in other programs, right? If you would do this not in the IPython shell, but in another program, it would be a file. And in this file, you would import this function like I did here, or with the abbreviation import as TST, right? Yeah, so with this prefix, we can distinguish different functions of the same name in different modules. We can also say help, right? So to see our help text, we would say, instead of calling the function, we would use that name as an argument to the help function. As you can see here, help of my function. And here you can see the text, right? This is the help text for my function. Q ends it. Yeah, so that works too. Yeah, so again, from import star is not what I recommend. Okay, yeah, and that's it for today. Thank you for your attention, and then see you in the question and answer round.